Hello everyone. Welcome to the third video in the scale factor stoichiometry series. In this video I'll be teaching you how to create mass balanced equations. These will be very important going forward, and so let's go ahead and get on with this. In order to be successful in this video, you need to understand what the mole is as a unit of measure, and that's something we talked about in the previous video, so I'm really hopeful that you're good on that one. And you should also be able to balance chemical equations and understand what that means. Now this third one is a real biggie here. You need to be able to determine the molar mass of a chemical from its formula. That's not something that I've discussed in either of these videos, but if you do not know how to do this, there will be some numbers that will be showing up later in the video, and you won't know where I got those numbers from. So if you do not know how to determine the molar mass of a chemical from its formula, let me invite you to stop watching this video for just a moment and go to the search feature and search for the phrase calculate molar mass of chemical, and you will find plenty of videos that will teach you how to do that. But if you already know how to determine the molar mass of a chemical from its formula, then let's go ahead and press on. After this lesson, you should be able to convert normal or mole balanced equations into mass balanced equations, and you should be able to explain the uses of a mass balanced equation. Let's go ahead and look at cookies again. In our first video, we had this cookie recipe where almost all of the measurements have been expressed as volume. Cup is volume, teaspoon is volume. The only one that hasn't been volume is eggs, where we've just counted them. It's very common for recipes in the United States to express the ingredients in volume, but it turns out that in a number of countries, it's more common to do it by mass. Here is the exact same recipe, but everything has been expressed in terms of mass, except again for the eggs, where we are just going to count them. So these are identical cookie recipes, just in one we have been measuring it by volume, and in the second one we're measuring it by mass. If you were to mix all these masses of butter and shortening and sugar together, and so on, you get the exact same recipe. So this is what we're going to be doing. We're going to think about the cups as perhaps being like moles, and the grams they'll just be like grams. So let's take a look at some mole balanced equations. There's our good friend ammonia synthesis again, as well as the rusting of iron. So there we have the balanced chemical equations where iron is rusting, and also we're making ammonia. If we were to mass balance these equations, they would look like this. 28 grams of nitrogen reacts with 6 grams of hydrogen to produce 34 grams of ammonia. Or for the formation of rust, 223.2 grams of iron reacts with 96 grams of oxygen to make 319.2 grams of ferric oxide, or iron 3 oxide. Let's go ahead and look at where these numbers come from and how you can figure those numbers out for yourself. So we need to create mass balanced equations by starting with the mole balanced equations here. In most textbooks, the equation for ammonia synthesis will look like this. And let's remember that that means 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to produce 2 moles of ammonia. What we need to do is change these mole measurements into mass measurements, and the key to that is the molar mass. So this is the calculation for turning moles of nitrogen into mass of nitrogen. You're going to multiply the number of moles that are in the equation, and that's just 1 mole of nitrogen, by the molar mass of nitrogen, which is 28 grams per mole. And this is the molar mass that I was talking about. If you don't know where I got that number from, please go do a YouTube video search for how to calculate molar mass of a chemical, and then return to this, and I hope the video will make sense from that point on. Then the moles of nitrogen will cancel, and we are left with grams of nitrogen. So this is not a scale factor, it's not dimensionless, it is 28 grams of nitrogen. 3 moles of hydrogen show up in our equation. When we multiply that by the molar mass of hydrogen, the moles of hydrogen cancel out, and we are left with 6 grams of hydrogen. And finally, for the ammonia, we have 2 moles of ammonia multiplied by the molar mass of ammonia. The moles of ammonia cancel out, and we're left with 34 grams of ammonia. And there we have the masses that correspond to the mole balanced equation. Now, here's the mass balanced equation written out as just one equation. 28 grams of nitrogen plus 6 grams of hydrogen goes to 34 grams of ammonia. And one really nice thing about mass balanced equations is you can check your work quickly by using the law of conservation of mass. The mass of the reactants must equal the mass of the products. If that doesn't happen, you've made a mistake somewhere. It turns out that all these mass balance equations must be perfectly balanced, as all things should be. Let's look at another example. Here is our rusting of iron again, and we will go through the conversion from moles of iron to mass of iron. And again, moles of iron cancel. Moles of oxygen will be converted to grams of oxygen, canceling the moles again. And finally, moles of rust will be converted to grams of rust. And we have our final mass balanced equation. Something I'd really like to point out to you here is that when you have converted from mole balanced equations to mass balanced equations, the numbers that were in the mass balanced equation replace the numbers that were in the mole balanced equation. So this 4 that's in front of the iron, that was 4 moles. We've changed that into grams, so that 4 isn't here anymore. This 3 that was in front of the oxygen, that was 3 moles. We don't need that 3 anymore. That is taken into account with the grams. Okay, similarly that 2 is the moles. We've taken that into account with the grams. So these numbers, when we go from moles to grams, this 4, this 3, this 2, we're not going to use them anymore. We now have the grams. If you think back to the cookie recipe, when you write the cups of flour and then change it to grams of flour, you wouldn't say 550 grams, 3 cups flour. Like you would just say the grams. All right, so these mass balanced equations created from the simplest mole balanced equations will be referred to as the standard mass balanced equations. Looking at ammonia synthesis, we have 28 grams of nitrogen plus 6 grams of hydrogen makes 34 grams of ammonia. And so those are the standard amounts. When we create scale factors, these will be the standards that we'll be looking at. And we'll be looking at scale factors on mass balanced equations very soon. Please take a moment and practice this skill. Here are some mole balanced equations for you. I have not written the word mole in there, but it is implied. That is 2 moles of hydrogen, 2 moles of water decomposing to make 2 moles of hydrogen and 1 mole of oxygen, and so forth with the others. So go ahead and pause this video, take a minute or two. That'll take you more than 2 minutes, I think. We got some big complicated chemicals showing up in that third one. So take the time as needed and pause this video. And when you come back, I'll have the answers for you. All right, welcome back, and let's see how you did. These are the mass balanced equations of the mole balanced equations that I just showed you. 36 grams of H2O will decompose to make 4 grams of hydrogen, 32 grams of oxygen. 88 grams of sodium azide will decompose to give you 46 grams of sodium and 42 grams of nitrogen. And finally, 65.4 grams of zinc reacts with 339.8 grams of silver nitrate to give you 189.4 grams of zinc nitrate and 215.8 grams of silver. And please do check, these equations do all mass balance. In all cases, the mass of the products does equal the mass of the reactants. And so that is a nice check to make sure that, well, we might still have done something wrong, but we made the same mistake twice. That's one. If they don't add up, you know you've done something wrong. If they do add up, you can't be sure that you've done something right, but it's usually a pretty good sign. Thanks for watching, and I look forward to seeing you again in our next video.